Good morning, everybody. The first press conference of this EGU2009 meeting. I would like to introduce to you David J. Hofmann from NOAA Earth System Research Laboratory in Boulder, Colorado, who's done a lot of research in Antarctica. And the title of his press conference is South Pole Ozone Hole Recovery. Ozone expected to begin recovery. Patient is not getting sicker. I think that's the
title of the press conference, the briefing.
Yeah. Okay.
This is the title of the
Right.
presentation
Okay.
that will be. There's a session at 5:30 today on polar ozone, and it'll be one of a number of papers. I think, looking at the title of the press conference and the information on it, indicates that this word recovery is very often, there are different meanings of it. Some people think recovery of the ozone hole, okay, it's gone. It's not going to be there anymore. But we know that this is a very long process. And so another way to look at recovery is, when does it look like it's beginning to get better? That's why I've used this sick person as a kind of a way to look at this. If you're sick, you're very happy when you start feeling a little bit better, but you're still not well. And that's kind of the situation here, is that while we know it's going to take a very long time before this ozone hole is totally gone, the fact that it's not getting any sicker, the patient. It's for the last 5, 6, 7 years, we don't see a continuing decline in the amount of ozone in the ozone hole. And I don't know how familiar you are with the science of ozone depletion and the ozone hole itself, and I'll be very brief because we don't have much time. But it's been shown that it's related to chemicals that are emitted at the surface by humans, of course. And these chemicals contain halogen gases, chlorine and bromine. And while they're very safe, they were invented after the Second World War for refrigerators, excellent for that. And the CFCs, as they're called, are not harmful by themselves. You can breathe them, you can eat them. They don't destroy ozone by themselves. But it was learned that what happens to them when they get emitted to the atmosphere, if nothing destroys them, they just float around, and eventually they work their way up into the stratosphere. And the ozone layer, of course, protects the planet from ultraviolet radiation from the sun. So these CFCs never see this ultraviolet radiation, but once they get up high enough, they start to see the ultraviolet radiation, which breaks them apart, frees the chlorine atom or the bromine atom, depending on what form it's in, and then it goes through a very rapid chain of reactions that destroys ozone. And so that's what's happening all over the world. It's not nearly as bad in this stratosphere over our heads here, because it's not as cold in our stratosphere here. But in the Antarctic, temperatures get down to minus 90 degrees Celsius. Clouds form in the stratosphere. When you fly in a high-altitude aircraft, jet liner, you normally don't see any clouds above you. If you could fly in the Antarctic stratosphere, or at the same level, and you could see anything, but in winter it's all dark down there, you would see clouds as high as you could go. And it's on the surface of these cloud particles that very unusual chemistry occurs. These molecules containing chlorine react on the surface. They have to have a surface. It frees reactive chlorine, which immediately destroys an ozone molecule. And then it regenerates itself. So one chlorine atom can destroy tens of thousands of ozone molecules, so it's very rapid. And so during the winter, the clouds are there, the chlorine gets activated, but it needs sunlight. The chain reaction includes photochemistry. So the atmosphere is all primed to go, and then the sun comes up in September, because it's the other way around from the northern hemisphere, and then ozone starts dropping. So this paper is about what can we learn from the rate of ozone loss as it starts going down in September. Is there something in there that helps us understand what's going on? And more important, is there something in there that will help us determine when it's going to get better? So first of all, let me demonstrate here. What I show on the left is an ozone profile, altitude in kilometers, 0 to 30, ozone pressure, that's how much ozone there is in a parcel of air, and you'll see that there's a nice big fat layer up here around 20 kilometers in the blue, and that's what protects us from ultraviolet coming down. This is a thermometer here that tells you how much total ozone is in this whole column, and so it's sitting up here close to 300. That's a nice healthy ozone layer. It protects us very well. Over on the right side is the temperature, which is a key also near the surface in Antarctica. This is at the South Pole in January, which is middle of summer, of course. It's quite warm at the surface, only minus 30 Celsius, and the stratosphere is very warm. And this tells you the coldest temperature that will be reached. And I'm going to start this running. Each of these profiles you'll see will be from a balloon sounding that our group made at the South Pole. About every 2 days they fire a balloon up and measure this profile. So you can see where the ozone is, how cold it's getting, and so on. Okay? So watch the date here. It's January, February. It's still quite warm. Now you're seeing the stratosphere starting to cool, temperatures dropping, getting colder, 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 colder. By May it's dark because it's the opposite of the northern hemisphere. Just stop it here. And you'll see that at this time, the red curve is the current temperature. The blue curve is the minimum that it reached at any time. You'll see that at the lowest point, we're at about minus 80, 90. At this point, all the water in the stratosphere condenses into ice. All the nitric acid vapor condenses into nitric acid clouds. It's a really weird atmosphere. And but there's no sunlight yet. It's still dark, so you're not losing this ozone. You see it settling somewhat. That's kind of natural in the low-pressure system over the pole, that as the atmosphere cools, everything in it starts settling down. So let's start running again now from the middle of winter. And we're into August now. We'll stop it there. And you see that September, at the altitudes of the ozone layer, sun rises about September 4th. So now it's starting to see sunlight up here, and it's still very cold. Lots of clouds around. It's still just getting light up there. And we let it run, and it goes down, and boom. All the ozone's been destroyed from 14 to 21 kilometers. Every single molecule. There's less ozone in this region here than we have in this room. That's very efficient, and that's because the chlorine reaction is so ferocious. It just destroys it all. And then we run it on. The sun is up now, and so it's doing other things to the chemistry. It's starting to warm the stratosphere dramatically, and then the ozone comes back in and fills up the hole. Not entirely. At the end of December, there's still a bite taken out here. And over the long term, we notice that in the lower stratosphere, there's been some decline in ozone. But this happens each spring. Boom, boom, boom. So this is kind of a diagram of what is happening there. This 2006 was the record ozone hole. This was the largest. This is a picture from a satellite. And the blue area is the size of the hole where ozone is below a certain value that's been established as the ozone hole level. It's about 220 Dobson units, but it's not important. Anyway, this area is larger than the area of North America, for example. You can see the continent of Antarctica there. And so we see a nice healthy ozone layer on the 27th of August, 1st of September, 6th of September, 9th of September, 18th of September, 22nd of September. So very, very rapidly. It goes to zero. So what we want to look at is what information do we have by keeping track of how fast this is happening. I should skip this one, but it just shows you what's the lowest that ozone has gone during an ozone hole since we started making measurements. 1986, we had quite a bit of ozone there, and then it went down for a period to where there was almost no ozone left in this 14 to 21 kilometer region. Then it started oscillating around, and some people said, oh, maybe the ozone hole is recovering. But then it went down again, now it's oscillating again. And what I'm going to show you is that there's no evidence that this is recovery. This is meteorology, a very disturbed situation. So let's go on. If you look at the amount of ozone as a function of day of the year, this is like early September here on through early October, you'll see that the ozone falls very rapidly from about 1 or 2 parts per million. That means of every million air molecules, only 1 or 2 are ozone. So it's a very rare gas. But still, that small amount does absorb the ultraviolet part of the solar spectrum. But then in about 10 or 15 days, it's come down a factor of 2 almost. This is an exponential scale. And the average rate of decline is about 12% a day, which is pretty rapid. So if you start out with 10 molecules one day, you have 9 the next, 8 the next, 7, 6, and then it just tails out. So it goes down pretty fast. And if you look at where is it going down the fastest, this is altitude again. This is the loss, this is the loss rate in percent per day. It peaks in this 16 to 18 kilometer region, very high, 20% per day. That's 1/5 of the ozone is lost in the first day, and then a fifth of what was left there, another fifth is what was left there. It's like uncompounding interest, essentially. So it's a very efficient process. This is looks complicated, but concentrate first on the red curve. This is the ozone loss rate, this percent per day I was talking about. So back in the early measurements, 1986, it was about 5%, and then it's increased on up to 10, 15%. This is just in this 14 to 21 kilometer band of ozone. And so what it looks like is that, okay, it got worse, 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 and then it stopped getting worse. And it's just starting to oscillate around. The other thing on here is these black dots are the area of Antarctica where the temperature up there in that stratospheric region is colder than 78 degrees. And why 78 degrees? That's because that's when clouds start to form. And so the ozone loss rate really picks up when these clouds start forming, and you can see some correlation between the number of clouds and the amount of ozone that's left. The bottom curve here is the amount of chlorine in parts per billion. For every billion air molecules, there's 1 chlorine atom, and that's been increasing gradually, but now is declining. Regulations put into place about 1995 or so has had an effect that some of the worst CFCs are now on their way down. But they have a very long lifetime in the atmosphere. They'll be there for a very long time. So you have to kind of put this all together and try to make sense out of it. And I'm not going to spend any time on the chlorine. The only key point is that it takes 2 chlorine molecules for this first reaction to go, or 1 chlorine and 1 bromine for that one to go. And we call that quadratic. It's not linear. Linear is if you double something, another thing will double. Quadratic is if you double it, the other thing will go up by a factor of 4. And that's what happens with chlorine. As you add chlorine, the first reaction that starts activating chlorine is quadratic. So you have to always think about a square when you're trying to model something like this. And so here we have the black curve now is what's observed in the loss rate. We started measurements in '86, and it started going up very rapidly, and then it tailed off. The red curve is this simple model where we assume a threshold of when there was enough chlorine to start just making an ozone hole, and then it increased, and it increased faster, and then it hit a saturation. At this point, the chemistry is so effective, it's just destroying all the ozone, and it's going to zero. And we can use that model then to extend it. What's going to happen beyond the last set of measurements in 2008? Well, this model would suggest that we're going to stay in this saturation mode for at least another 10 or 20 years. And that's why there's a little confusion, because we expect, you said, the ozone layer to start recovering, or to recover in 10 or 20 years. We really expect it to begin to recover. Here, the ozone loss rate begins to drop. And that's the key of this talk, is we think the patient will begin to say, gee, I feel better today, in about 20 years. And then he will, on an exponential sort of basis, get to feeling better and better and better, until way down here he feels almost as good as he did before he got sick. But you know, as you get older, you never feel better than you did when you were young, and you're always getting older. So and this is true too here, the patient may never come back to where he was. But there are climatic effects which suggest, gee, the patient might end up to be better than he was before he got sick. And so there's a lot of complicated chemistry involving if the stratosphere gets cooler and if the troposphere gets warmer with global change, that ozone may not recover to where it was before. But that's a very deep topic which I really don't want to go into. And so summarizing, we feel that the ozone loss rate in the heart of the ozone hole can be adequately described with processes that we know about. There's nothing missing, no secrets. We know the chemistry pretty well. We know why it probably hasn't gotten worse over the last 10 years or so. But there's no sign yet of this beginning of recovery. We're watching for it, but it hasn't begun. The patient hasn't begun to get better yet. We expect that to happen somewhere around 2030. It could be 5 years earlier, but that will be the first sign. And from then on, once it starts getting better, we know that it will continue to recover. But this full recovery is still not expected till 2065, another 55 years, when the ozone hole will be totally full, the sun comes up, and it won't go down anymore. So I think I'll stop there.
Thank you very much, David. Are there any questions from the room?
Can you tell something about the possible effect of the ozone hole on Antarctic climate and the possible melting of the Antarctic ice sheet?
Whether the ozone hole will affect Antarctic climate. It's a complicated issue. There's been, the question is the ozone hole causing climate change? I've been asked that, and the answer is no. They're related, but they're not directly related. Global climate change is caused mostly by the increase in carbon dioxide, as you well know, and other gases. But the ozone hole has changed the meteorology in Antarctica. It's actually cooled the stratosphere because ozone absorbs sunlight. So if you remove some of it, the stratosphere will not get as warm as it did before. And that will affect the circulation of air. And it's been found that that is related to the fact that, while the Antarctic plateau does not seem to be getting a lot warmer, the peninsula, that little tail that sticks out, is outside of the ozone hole. And there, because of meteorology, it's actually getting warm quite rapidly. And so they're related in that sense, but the effect on the ozone hole itself is that as the surface gets warmer, the stratosphere cools. There's a balance of energy there. If the stratosphere gets cooler, you can have more clouds form. If you have more clouds form, you can activate more chlorine. So in that sense, global warming will probably run the ozone hole out a little bit longer, but it's not much. We can estimate it. 1 or 2 years longer due to the climate change that we expect by 2050. So while they're linked, and scientifically it's very interesting, I don't think there's a big calamity or connection that the ozone hole is going to make climate worse or climate is going to make the ozone hole worse. They're linked, but they're not strongly coupled. They're kind of related.
Colin Giermeier from Nature. Can you perhaps say a few words about the main discoveries that scientists have made about ozone chemistry and likely rate of ozone recovery in the last couple of years, say? Are there any things we think we know now which we haven't known before, around 2006, 2005?
Yeah. 3 or 4 years ago, if I was giving this talk, and I probably did, I would have said that we probably will detect this patients getting warmer in the next few years. And the ozone hole will probably be totally gone in another 30 or 40 years. And now that has changed, and it's not been yesterday. It was more like a couple of years ago. The realization that the time it takes for all this stuff that we're emitting in the northern hemisphere to get into the Antarctic stratosphere is quite a bit longer. We thought maybe 2 or 3 years. Not going to take long. But what it has to do, it has to diffuse up into the stratosphere. That might only take a couple of years. But then it has to go all the way down to the southern hemisphere, and it has to come in at very high altitude then, and through thermodynamics, and it has to get back down into the lower stratosphere. And the estimate now is that might take 5.5 to 6 years. And so that's extending things out somewhat. It's slowing the whole process down, so that now instead of expecting to begin to see the ozone hole get smaller in the next few years, we're thinking more, like I just said, the next 20 years. And the full recovery now, instead of maybe 40 years, is more like 55, 60 years. So that's been the major realization for the ozone hole, that it's going to be around much longer than we expected. But for us scientists who love to go to Antarctica and measure stuff, that's job security, kind of, so it's not going to be gone. And then they say, well, why are you going down to Antarctica to study this thing? And you might say, well, if it's there and you're saying that it's going to go away, and you're measuring these other gases, don't you believe it will go away? Yes, we do, but there's nothing like verifying it, that it really is gone. So the laboratory I work for has been in business for a long time. Its forerunners go all the way back to the start of the Mauna Loa CO2 record. Dave Keeling started in 1958. The U.S. Weather Bureau supported that, and that became another agency. And finally, in 1970, the National Oceanic and Atmospheric was created. But they operate these observatories at Alaska, Mauna Loa, Samoa, and the South Pole, where all these measurements are made. And so we have some very long records. And there were times when people asked, why are you measuring ozone at these places? That was before there was any ozone destruction. I said, well, it's important to monitor anything in the atmosphere that you can, because it might change. And you need to get an early warning when something's changing. And if we wouldn't have had that attitude, we wouldn't know that carbon dioxide was causing a problem until we got well into it. And the same with ozone. Somebody suddenly said, geez, the ozone layer's down. And over the rest of the latitude, it's only 5% down. just say, well, it's not bad. But in Antarctica, by this time, it's down to half of the layers gone and further. So if people wouldn't have been making those measurements, if Joe Farman from England hadn't looked very carefully at his Dobson spectrophotometer data back in 1980-81 and saw peculiar, in October, I got 20-30% less ozone than I did 5 years ago. And that got other people interested, and the satellite people started looking at their data. Oh yeah, man, it's happening all over Antarctica. And so if you have the data, you can go back and look at these things. And that's the key thing about monitoring. You can never go back and get that data. You can study a process like in a laboratory. Does chlorine destroy chemistry? You can do that in a laboratory. But you can do that anytime. You can do it tomorrow, you can do it next week, you can do it a year from now. But monitoring, you can't go back and make a measurement of the way the atmosphere was 20 years ago. And so when somebody asked me, why do you continue to make these measurements? Nothing's changing. It's boring. I said, no, it isn't. It's very interesting. And it's great if nothing changes. If things start changing, then, you know, quite likely you've got a problem. Very seldom do you see something change in the atmosphere that isn't being caused by man and that is beneficial. So.
Oops. Hello, Dagmar Röhrlich for the Deutschlandfunk. Some weeks ago there had been an article from, I think, Chinese scientists, and they claimed that the ozone hole could recover quite fast because of climate change. They told us in this article that the circulation patterns would change because of the warming in the tropics, so that the tropics would prevent this polar vortex from forming or to be as stable as he used to be, and that this would help us with the ozone hole. What do you consider about this theory?
Again, by looking back to the long-term measurements, we do see a correlation between the wave activity and how cold the Antarctic stratosphere gets. That's the key. If it gets very cold, then this Antarctic vortex will be very stable, as it has been for last 10-15 years. If you go back farther, before it got that cold, there were some oscillations in the size of the vortex. But there also was recently, in 2002, this stable vortex suddenly one year broke in half. And there were two little ozone holes, and one went off and the other one kind of reformed right out of nowhere. So it wasn't caused by a trend of anything. It was just unusual meteorology. So you expect that to happen every once in a while, and in this model we just repeat what the temperatures did the last 30 years for another 30-year period, another 30, just assuming that the variability will continue. But I'm not familiar with, and you say that there is some evidence they have that you would have to have an increase in the amount of atmospheric wave activity, which would cause the vortex to be more disturbed. Now, heating the atmosphere presumably could affect that. However, there is no evidence, direct evidence, that that has happened since global warming began, which has been going on now for 10-15 years, that it's been clearly increasing the temperature. So while a model might, I suspect that this was a model study in which they tried to model the atmosphere and found that there would be an increase in wave activity, which would make the Antarctic stratosphere more unstable. I agree that that's a possibility. But again, we can only rely on the measurements that we have so far. But it's good to try to model what might happen. So I myself have no evidence that that is happening at this time.
Liz Gallagher from Environmental Research Web. Could you comment about the impacts of the ozone hole and how they will change as it recovers?
Would you repeat the last part?
Could you comment about the impacts of the ozone hole and how those impacts will change as the hole recovers?
From a biological point of view, there have been some studies of the increase in UV on zooplankton, phytoplankton, and so on in the waters. And UV does penetrate into the water somewhat, but the studies that have been done to date, I don't think have really mapped out sufficiently what is happening around Antarctica. I think experiments in the laboratory suggest that there can be changes to organisms due to elevated UV. There's one fortunate thing about this happening over Antarctica, and that is that the sun is always at a very low angle. So even though your ozone layer might be down by a factor of 2, you don't have the overhead sun. So when the sun is near the horizon, it has to go through a much longer path of the atmosphere. You think of a slice. If the sun's coming straight down, it only has to go through that much. If the sun is over here on the horizon, it has to go through that much. So that helps a lot. Yet there are measurements of elevated levels of ultraviolet radiation in the springtime, not only in Antarctica, but for example at Ushuaia in southern Argentina, on the southern tip of South America, where as this ozone hole, the extremities of it, it might get kind of egg-shaped and it rotates around the pole, and for a few days the low ozone passes over some of these regions. And certainly if you had continued exposure to this kind of radiation, it would certainly have long-term effects. People talk of increased incidence of skin cancer, cataracts, things like that. But in all cases, there's no continual exposure of this radiation to people or animals, and the same with the ozone hole. It only lasts for a month or two. And so by the time midsummer comes around, when the sun is still not overhead, but it's up pretty high, the ozone hole is closed, as I showed in that movie. So the expected effects of high levels of UV are there, but they're not extremely deleterious at this time.
Thank you very much. Are there any more questions? In that case, we will close, and I'm sure there will be opportunity to make an appointment for an interview with you. Okay, thank you very much, David.
Thank you.